Welcome to the Scientific Sense podcast, where we explore emerging ideas from science, policy, economics, and technology. My name is Gil Eapen. We talk with world's leading academics and experts about their recent research or general areas of topical interest. Scientific Sense is an unstructured conversation with no agenda or preparation. We cover a wide variety of domains where new discoveries are made and new technologies are developed on a daily basis. We are most interested in how new ideas affect society and help educate the world how to pursue a rewarding and enjoyable life rooted in science, logic, and information. We seek knowledge without boundaries or constraints and provide unedited content of conversations with researchers and leaders who love what they do. A companion blog to this podcast can be found at scientificsense.com, and this podcast is available on over a dozen platforms and directly at scientificsense.net. If you have suggestions for topics, guests, and other ideas, please send them to info@scientificsense.com, and I can be reached at gil@eapen.info. My guest today is Professor Richard Lebed, who is Professor of Physics at Arizona State University. His research involves studying the properties of and interactions between particles at the most elementary level. Welcome, Richard.
Thank you. It's a pleasure to be here, Gil.
Yeah, thanks for doing this. So our discussion today, you have a review article entitled Heavy-Quark QCD Exotica. And then obviously you go through a lot of details of elementary particles here. In the abstract, you say this review presents an overview of the remarkable progress in the field of heavy quark exotic hadrons over the past 15 years. And so obviously we have gone through a lot of discoveries, lot of ideas in particle physics. When I think about this, Richard, it seems like we started with earth, fire, and water as fundamental particles. That was a long time ago, and then we found atoms. Atoms were the fundamental particles. And then came electrons, protons, and neutrons. Now physicists are saying neutrons and protons are not it, right? There are stuff inside it. So it sounds a bit like the Russian doll trick. Are we close to getting the last one?
Well, the great thing is we'll never know for certain if we've gotten the last one. Now, that being said, as far as we know, and people do experiments to try to find out if there's a substructure inside of these quarks and gluons that are sitting inside of protons and neutrons. But as far as we know, there's no real hint for substructure within those yet.
And neutrons and protons we can see, but the quarks, the fundamental particles inside protons and neutrons we cannot see. So could we verify them experimentally?
Oh, absolutely. And, there's no reason you should believe in them unless you have some way of checking. So let me give you an analogy to the way we think about the fact that there is substructure inside of protons and neutrons. It would be like saying, okay, I have a box and that box is completely sealed. And no matter how hard I try, I can't cut it into pieces to see what's inside, but I can shake it and I can hear that it's rattling. And that rattling gives me evidence that there's something inside of it. Now, of course, that's a gross oversimplification, but it gives you an idea of the fact that there are certain indirect things that you can do to prove that something has a substructure, even if you can't prove that substructure is there by actually breaking it into those pieces.
Yeah. I can't quite remember the scale of this, Richard. So approximately 10 to the power minus 10 centimeters for the atom, and 10 to the power minus 13 for the protons and neutrons. And then you have to go 3 orders down from there to get to the quarks, right? Something along those lines?
It's, let's see, if you're doing centimeters, it's 10 to the minus 8 centimeters for atoms. And you were correct, it's 10 to the minus 13 centimeters for atomic nuclei, protons and neutrons. So the nuclei are about 100,000 times smaller than the atoms that contain them. So that's quite a big scale difference. And you would say, well, wait a second, I remember from high school science when I was learning about the atomic model that like charges repel and unlike charges attract, but a nucleus has a whole bunch of protons in it, and those protons are all positively charged. So what is holding them together into that tiny little space? Certainly not electricity and magnetism. That's working against you. And that gives you evidence that there is a much stronger force that's keeping them bound together inside the atomic nucleus. And that's what we call the strong nuclear force.
Right. So that's the crux of so could you define hadrons? Everybody has heard of the Large Hadron Collider, where we collide protons to find other particles. So what's a general definition of hadrons?
A hadron is any elementary particle that, more specifically, any subatomic particle that feels the strong nuclear force that we were just talking about. So in particular, protons and neutrons are particular types of hadrons, as are things you've heard of called maybe pions and other mesons. So anything that would feel the strong nuclear force by definition is a hadron.
So famous hadrons, so to speak, are neutrons and protons. Are there substantial other hadrons that, substantial meaning, does it, do we deal with them frequently? Any other hadrons?
Well, the question is, what do you mean by frequently? So for example, one way at a sort of a superficial level of understanding what it is that's holding protons and neutrons together is that they are exchanging lighter hadrons called mesons, and in particular pions. And that's an idea that came from the early 1930s. And the interesting thing about the way that particle physics is done is that was a very successful idea, and it worked for decades until people were able to develop accelerators that could go much, much deeper into the structure. And then they found that the protons and the neutrons, and indeed these pions and other mesons themselves, have a substructure, which is what quarks and gluons are all about.
Okay. And so the question that you posed at the beginning, it's a puzzle. You have multiple protons in the nucleus, except for hydrogen. Multiple protons, they carry positive charge, and we learned that they repel each other. So how do they actually remain in the nucleus at such short distances? And so that's a trick, right? That is what you're talking about.
Right. And that's what I was referring to when I said that the earliest successful, at least partial picture of what was going on is the idea that the protons and the neutrons are exchanging these mesons, and those mesons are carrying the strong force attraction between them. Now, nowadays, we know that if you go deeper into them, that's when you start to see, and what's going on is that when you're exchanging a meson, you're exchanging pairs of quarks, and you're exchanging gluons. And so it gets more and more and more intricate as you go deeper and deeper into it. And so that's the essence of the kind of particle physics that I focus on, is to understand aspects of strong interaction physics.
Yeah. So could we get into the details of quarks then, Richard? So there are a variety of quarks, right? And we have a reasonably good idea how the neutron and proton are constructed from quarks.
Mm-hmm. Yes, we don't have a perfect idea, so that's an active area of research, but we do know an awful lot about it. So we talk about protons and neutrons having a certain number of valence quarks. And that term valence is analogous to the way that people in chemistry talk about valence electrons. In that case, they're talking about a whole atom and they say, oh, okay, well, we know that an atom has a whole bunch of electrons, but most of them are sitting in closed and chemically inert shells where they don't like to interact with other atoms, but it's only the top ones, only the least tightly bound ones that like to engage in forming molecular bonds. And something analogous happens with protons and neutrons that, for example, a proton has two quarks that are called up-type quarks. That's a particular species of a quark, and one down quark. So those are the three valence quarks inside of a proton. But it turns out that if you look at the masses of those quarks, they only account for a few percent of the mass of the whole proton. And what's going on there is that because the strong nuclear force is so very strong, what's going on is that these quarks are kind of like flies in amber, that they're passing gluons back and forth, the force carriers of the strong force, and the gluons are interacting with other gluons. And there is so much force exchange going on that the energy associated with this binding creates a mass equivalent through E equals mc squared that generates a very substantial mass, a much bigger mass than the mass of just these valence quarks.
Yeah, that is so interesting, Richard. So if I understand this correctly, the size of the quark is at least 3 orders of magnitude smaller than the diameter of the proton, right?
The masses. We don't know about the actual size of a quark. As far as we know, it could, in principle, be a geometric point. So we don't know of a physical size to it. But in terms of mass, it is. Yeah. It's orders of magnitude smaller, or at least for the light ones that make up the valence quarks of protons and neutrons.
Yeah. So the valence quarks, as you say, are 2 up quarks and 1 down quark for the proton. So those are the things that we can, in experiments, sort of, if we pry open a proton, those are the things that come out. But they don't, as you say, account for a large part of the mass of the proton, only about a few percentage points. And so if I understand this correctly, Richard, so most of the mass of the proton is sitting in the energy inside the.
That's exactly right. It's sitting in the mass equivalent of the energy field of this strong interaction glue. These gluon exchanges. And it gets even more interesting than that, because since these gluons, these force carriers of strong interaction physics, have such strong couplings, they can pop extra quark-antiquark pairs out of the vacuum that only live for a very small amount of time and before they collapse down again. So the actual content of a particle like a proton or a neutron, as far as we know, is these valence quarks that only account for a percent or a couple of percent of the mass of the whole thing, a lot of energy sitting in the glue, and in terms of these what are called virtual quark-antiquark pairs that are always popping in and out of the vacuum. The analogy I like to give my class is, it's like you were to go to the pub and you get a pint of beer, and you're looking at it and you say, okay, that beer has a head of foam on it, but if I look at the beer closely, I see that foam is coming from bubbles that are coming up from the bottom. And any one individual bubble is going to nucleate at the bottom, it's going to rise up to the top, and it's going to pop a couple of minutes later. But for a decent amount of time, even though those individual bubbles have very short lifetimes, for a long amount of time, the content of bubbles within your beer is going to be a fairly steady amount. And that's the sort of thing that's going on with these virtual quark-antiquark pairs inside of a proton or a neutron.
So is it analogous to, I know, Richard, in space, we have this quantum effects of quantum particles popping in and out in complete vacuum. It's sort of a similar situation inside a proton?
It's exactly the same thing. It just happens more frequently inside a proton or a neutron because there's so much energy available. You're no longer in, the vacuum of empty space. You've got this ambient energy, and so it becomes much more frequent that this sort of thing is happening. But it's the same mechanism, and it all comes back to, basically, it comes back to the uncertainty principle of quantum mechanics that this is possible.
And so when a particle, antiparticle, a top quark and an anti-top quark pop out of no, not necessarily a vacuum, but pop out of the proton environment, so to speak, there is no mass created, right? They equally cancel?
Well, first of all, you said top quark. Those are the heaviest of all the flavors. Much more frequently it'd be up and anti-up. And yes, I know it's kind of confusing that we have a quark called an up and a quark called a top, but that's just the nomenclature that we're stuck with. The people who originally named them wanted to call the top truth instead, and that never caught on. But in any case, your question was, wait a second, how can you just create mass out of nothing? The point is that these virtual particles have the property that they do not have to satisfy the Einstein relation between energy and momentum and mass for a very short amount of time that is consistent with the Pauli exclusion principle of quantum mechanics. So yes, if it were possible to actually grab one of those quarks and yank it out of there and say, aha, I've got it, and you just created mass out of nothing, well, the very nature of saying you have a virtual particle means no, because of quantum mechanics, you can't just yank it out of there and it's going to stay there in your hand. So there's no mystery with regard to, am I really conserving energy? Am I really conserving momentum? That's all taken care of.
That's all taken care of. So the structure of the proton, again, two up quarks and one down quark. So they are in some sort of configuration inside the proton, right? So can you separate them somehow?
Well, I'm not quite sure what you mean by separate, because again, you can't pull one out. But the way that people actually proved the existence of these dynamical objects called quarks was basically by a version of what's called Rutherford scattering, the way that people proved the existence of the nucleus, which was, in the case of Rutherford scattering, they fired charged particles at atoms that, were big fat alpha particles, the same ones you would learn about in radioactivity. And they would just tear through the atomic electrons, and they would hit the nucleus and bounce off of it. And so by finding out the pattern, the angular distribution of how they were bouncing off, people were able to figure out, oh, okay, so the atoms have this very dense charged nucleus. Well, in the case of proving the existence of substructure of individual nucleons like protons and neutrons, they used a much higher energy beam, and they found that if you get it up to an energy where you can probe inside of the protons or neutrons, it doesn't look like just firing bullets at a glob of clay. You actually get a pattern that's consistent with you having bounced off of these point-like charged objects inside of that, even though you can't actually pull the charged point-like object completely outside of it. So that's called deep inelastic scattering because, well, deep means that it used a lot of energy. Inelastic means if you hit a proton that hard, it's probably going to fly into pieces, and not a substructure. It's going to create new pieces, and that's called inelastic scattering. So this is how it was proved in the first place that there were such things as quarks.
So this was, when was this proved?
That was done in the very late 1960s. So the history was that there were these two Caltech physics professors, Murray Gell-Mann and Richard Feynman. And Feynman, of course, is Feynman of what are called Feynman diagrams, which I'm sure everyone's seen at some point in their life. Murray Gell-Mann was the guy who came up with the idea of the quark model. And Feynman was always very critical of this and said, how should I treat it if you're telling me that there's these substructure pieces inside of protons and neutrons, but you can't actually pull one out of it? And so he came up with an idea that, well, if you scatter, if you hit the protons or neutrons with beam particles, you might be able to prove the existence of substructure through looking at what the ejecta looks like. So he was the one who inspired these ideas.
Obviously, we didn't have LHC then. In the 60s, did we have Fermi?
Fermilab? Fermilab came online in, I believe, the late 80s.
No, I was wondering. I mean, how did they? Could they run an experiment at that time?
Oh yeah. I mean, in the 60s, basically, the history is that after the end of World War II, the U.S. government was so grateful to nuclear scientists for the Manhattan Project that they poured energy into them being able to do basic research, and that's when big science really took off in the sense of being able to develop accelerator facilities. And almost instantly, as soon as these things turned on, people started finding more and more and more and more new particles. So yeah, there were experiments that were being done all over the U.S. Up through the time of, say, these deep inelastic scattering experiments. And as time went on, as the experiments required greater amounts of energy in order to probe deeper, to probe at higher energy levels and at higher mass levels, they became more expensive, and it became necessary for individual universities that originally had their own machines to work together to form consortia to develop bigger machines so that they could do more involved experiments.
Okay. And so going back to the protons again, so these quarks inside the proton, they are exchanging gluons, you said. So it's a bit like, would it be a correct term to call it a gluon, some sort of plasma in which the quarks are sort of swimming?
It's not unreasonable to call it that. There actually is a technical term called quark-gluon plasma that is associated with where you have a soup of quarks and gluons, but they're not necessarily associated with any single hadron. So there are experiments that people do to create quark-gluon plasma and study the properties of this sort of generalized, strongly interacting matter that has a greater extent than just the inside of a single hadron. But it's not unreasonable to say that I have some sort of, if you will, soup of quarks and gluons inside of a hadron.
Yeah. And so the gluons, are they particles as well?
Gluons, okay, so here's the story. The way we understand fundamental forces, especially when you're talking about how they work at the subatomic, is that they all seem to fall into a certain category called a particular type of quantum field theory, and specifically what's called a gauge theory. And the interaction is one of particles exchanging special particular particles called gauge particles. So in the case of electricity and magnetism, the associated quantum theory, quantum field theory, quantum gauge symmetry is called quantum electrodynamics. And the way we understand that is that everything you know about electricity and magnetism at its most fundamental level is associated with particles carrying electric charge that exchange force carriers, which we call photons. Now, most people have heard of photons. You say, well, photons are just particles of light. That's what, is hitting your eye coming from the sun. Absolutely true. But it's also true that when you have two charged particles and they're attracting or repelling each other, what they are really doing is they are exchanging virtual photons between them. So now, to directly go after your question, what about these gluons? Well, gluons are the analogous force carriers of the quantum field theory of strong nuclear interactions, which is given the name of quantum chromodynamics. So quantum chromodynamics is the theory that says, okay, strong nuclear interactions come from particles that carry their own kind of charge, which is called color charge. That's a semi-whimsical name because it has nothing to do with literal colors of light. But any particles that carry color exchange force by exchanging the gauge particles, the force carriers of QCD, which are called gluons. So this business about not being able to break up an individual proton or neutron and look at the individual quarks has a name. It's called confinement. And the way that we define it is to say any particle that carries an actual net color that isn't a compound that overall is color neutral, you can't see that by itself. It is only, you can only see combinations of colored particles when their overall color charge is 0. And so that's the case for a proton or a neutron, but a quark carries color and the gluon carries color.
Okay. So if I understand this correctly, Richard, so going back to the electrons, they use photons as a way to essentially communicate them. And the photons, just like we have the particle wave duality on the photon, it sort of behaves both as a particle and as a wave. That's true, right? And so we have a sort of an analogous situation inside the proton. So gluons are a bit like that.
That's absolutely true. And that's true for any of these particles I've been talking about. Every single particle in the universe has that quantum particle wave duality to it. I mean, even, you could say that we as particles, we humans as particles, also have a wave nature to us, but you can calculate what the associated quantum mechanical wavelength is, and it turns out to be absolutely tiny, something like 10 to the minus 30 something meters. So the way I think about it is that quantum mechanics is not just some weird things that only happen when you go to the subatomic level. It's that they become really pronounced when you're at the subatomic level. And once you start looking at things that are mesoscopic or macroscopic, it becomes much harder to find the residual effects of it.
So just like the photons allow electrons to communicate, the gluons carry sort of a color charge, and they allow the quarks to communicate or essentially to stick together.
Right, very close. Yeah. So the quarks carry a color charge, and they communicate with each other by passing gluons back and forth.
Okay. The gluons don't have color charge.
Interesting you should ask that. It's a weird feature that distinguishes electromagnetic interactions from strong interactions in that photons are electrically neutral, but they couple to any particle that carries electric charge. On the converse side, quarks carry color charge, and gluons actually themselves also carry a color charge. So not only can gluons couple to quarks, which is what we've been talking about, gluons can actually couple to other gluons. And that seems to be one of the ingredients explaining why it is that it seems to be impossible to yank a quark or a gluon out of a proton or a neutron. So there are interesting similarities and interesting differences between quantum electrodynamics and quantum chromodynamics.
And so that's the basis of the strong force. In terms of, sort of the orders of magnitude, how much stronger is it compared to an electromagnetic force?
The only thing you're looking at is you're saying, I'm gonna compare two an electron and an anti-electron an angstrom apart, and a quark and an anti-quark an angstrom apart, and just work out what the strength of the force is, you'd find it's something on the order of 100 or several hundred times stronger for the strong force than it is the electromagnetic force.
Okay, and it doesn't degrade by distance, right?
Oh, it very
The strong
definitely
force?
does. So think about it this way: since
Oh,
all strongly interacting particles should feel the strong force, like protons and neutrons, if it didn't degrade by distance, then if you had two atoms side by side in a molecule, then the nucleus of one and the nucleus of the other would tend to either be strongly attracted to each other or strongly repelling each other, which would mean that chemistry wouldn't work because you wouldn't be able to form compounds. It's another interesting feature of the strong force that it's extremely strong, but once you get up to distances that are a little bit bigger than the size of an atomic nucleus, they tend to fall off much faster than electromagnetic forces, at least when you're talking about color, neutral color zero objects like hadrons, like protons and neutrons.
right. Okay. So extremely strong in very short horizons, almost like the exact opposite of gravity.
I suppose so. I suppose you could say that. Now, there's a difference, and I've seen that you've talked to people who've, talked about things like gravity, a large scale, and string theory. No one has ever been able to come up with an appropriate quantum theory for gravity, which is its own kettle of fish, and that would be, its own podcast.
Yeah, I haven't done that. So gluons and quarks inside the proton and neutron, and then you touched on this inside the atomic nuclei. You have multiple protons sitting there. So there's another phenomenon going on in terms of interactions between protons. You call it
yes. So you asked earlier, well, do I really have to worry about any hadrons in everyday life apart from protons and neutrons? And the short answer was, well, if all you're talking about are stable particles that you encounter on a day-to-day basis, yes, those are the only ones you see directly. But a way of understanding how they are attracting each other is by means of the exchange of mesons, which again, at a deeper level, we now understand is actually that they are exchanging quarks and antiquarks.
So that interaction is obviously quite different from the interaction inside the proton, right? So how does that differ? I mean, obviously, different particles or different fields. How does it differ in terms of the strength of that interaction and what?
Well, here's an analogy to think about this. The analogy again would be, say, in atomic physics, in chemistry, molecular physics, and you say, okay, well, I know that there's this strong attraction. Now that we've talked about strong force, it's nowhere near as strong, but there's this electric interaction between an electron and the positive nucleus of any atom. Now, suppose I look at a molecule that each of, and all of its atoms are individually neutral atoms, but it's still held together somehow. In that case, what it's doing is it's exchanging pairs of electrons, that sort of thing. And in chemistry, people talk about residual or van der Waals interactions between atoms. Well, the difference here is the analogous thing in terms of hadronic physics would be to say, okay, well, in an atomic nucleus, you have this big cluster of protons and neutrons, each one of which you could take out separately, each one of which is a color neutral object, but they still have these residual strong interactions between them, which is what's responsible for holding together the nucleus. And a convenient way of depicting that is by means of thinking about meson exchanges.
Yeah. Is the meson exchanges, can it be considered sort of an extension of the phenomenon we talked about inside the proton?
Right. It's a residual interaction involving quarks and gluons because, of course, the mesons themselves are hadrons, so they have quarks and gluons inside of them. So it's a convenient way to effectively describe an interaction.
Okay. And so this is why we call this whole field a quantum chromodynamics. So that's because we
Exactly.
call all
Chromo
these
referring to
colors, right?
colors.
Even though they, yeah. So QCD. Now the review article is a lot about you call it Heavy-Quark QCD Exotica. So we haven't talked about the other types of quarks other than the up and down. So as we go up that scale, you have much
That's right.
heavier
That's right. And
quarks.
so you remember we were saying earlier that the up and the down quarks only account for something like 1% or so of the mass of a proton or a neutron. There are quarks that are many times heavier than that. So the next one up in mass is called a strange quark, and then after that you have what's called a charm quark, and then a bottom quark, and then finally a top quark. And unlike what we were talking about before, when you have a hadron that has, for example, a bottom quark or a charm quark in it, in those cases, those heavy quarks really do make up a much larger fraction of the total mass of the whole hadron that they live in. So what it basically is saying is that the typical scale of the kinds of energies that are associated with all of these multiple gluon exchanges inside of hadrons is somewhere in between the mass scale of the lightest quarks and the mass scale of the heavier quarks.
So this should give us. So do we get an understanding of? So let me ask you differently. Are there protons where you have, instead of the up and down, you have the top and strange and other heavier
Yes, but we don't call them protons.
There?
Every time you make an exchange of one quark flavor, that's the terminology, for another, you produce a different kind of hadron. So, for example, if you were to take a proton and you were to take out one of its down quarks, or one of its up quarks, and replace it with a strange quark, you get a different kind of hadron called, say, a sigma baryon. Or if you replace it with a charm quark, you start creating things called lambda C baryons and so forth. And so each one of these permutations of the different combinations of quark flavors corresponds to a different particle with different attributes. There are relationships between them, but you have to go off and measure what is their mass, what is their coupling to other particles, what is its lifetime before it decays. And yes, you can hope to be able to predict some of those things based on your theories, but you have to go off and measure them as well.
Right. Yeah. Richard, we'll take a quick break.
Okay.
When we come back, we'll talk more about this.
This is a Scientific Sense podcast providing unscripted conversations with leading academics and researchers on a variety of topics. If you'd like to sponsor this podcast, please reach out to info@scientificsense.com.
So we're back. Richard, we were talking about the fundamental particles, hadrons, like neutrons and protons. We can peek inside them and we find even more fundamental particles. Quarks inside protons and neutrons, they have something called gluons that they use to essentially communicate and stay together. The typical quarks, the up and down quarks that make up the proton, just account for a very small part of the proton's weight. And so most of the mass, I should say, is sitting in the energy inside the proton. And we talked about why protons sort of stay together in atomic nuclei, and they are exchanging mesons, which are also hadrons, to accomplish that task. But part of your research interest is thinking about other varieties of quarks inside these particles. They're not necessarily protons, but other types of proton-like particles. And maybe even configurations that we expect in a proton from something different from that as well, right? So before we get to the details, Richard, what is a heavy quark?
A heavy quark just refers to a quark that has a mass larger than the energy scale divided by the speed of light squared, according to E equals mc squared, that is typical for the energy of the glue fields inside of a hadron. So to be more specific about what we were talking about in the first half, an up quark or a down quark has a mass of about 2 to 5 million electron volts divided by the speed of light squared, whereas the typical gluon energy scale is something like 100 million. So a heavy quark would be a quark whose mass expressed in terms of energy equivalent would be larger than that 100 million electron volts. So that would specifically refer to, say, charm quarks, where it's something like 1,500 million electron volts per c squared, or a bottom quark where it's something like 4,000 or 4,500 million electron volts per c squared. So you mentioned my review on Heavy-Quark Exotica. We're specifically talking about hadrons that contain these charm quarks or these bottom quarks.
Yeah. And like you mentioned in the first half, so if we take the up quark or the down quark and replace them with, let's say, strange or a charm quark, they won't be protons anymore. They will be some other particle.
Right.
And we have seen these particles in LHC.
Oh yes, we've seen these particles since the 1950s.
Oh wow! Yeah.
So in some of even these smaller experiments that I was talking about, which would be hosted at individual universities, it really, we knew about almost all of the fundamental particles before the LHC ever turned on. The only truly fundamental particle that's been discovered at the LHC is the Higgs boson. But there are tons and tons and tons of other interesting hadrons in particular that have been discovered at the LHC. In fact, I saw an article by a friend of mine who works there, and he's keeping track. He says there are now 59 new hadrons that have been discovered at the LHC. So it's quite a zoo.
Yeah. Yeah, I mean, you have so many different permutations.
Exactly.
Right? So it looks like all those permutations exist, albeit in the grand scheme of things, very small chance for those things to exist, right?
How do you mean very small chance?
I mean these exotic varieties compared to the regular stuff.
Okay, so now it's time to finally define what's meant by an exotic hadron. Yeah. Okay, so we've talked for a while about protons and neutrons, and we've also talked about mesons. Now, protons and neutrons, we said, have 3 valence quarks in them. And all hadrons that have a net number of 3 valence quarks are given the name of baryons, whereas all hadrons that have a net number of 0 quarks, because, for example, they have a quark and an antiquark, which gives you a net quark number of 0. Those are called mesons. And from the time that it was appreciated that there were such things as quarks and antiquarks, when Murray Gell-Mann invented the quark model in 1964, independently of a fellow by the name of George Zweig, it was found that every single hadron found for the next 50 years, all the ones before that, and then all the ones for almost a half century after that, were in only 2 varieties. They were either these 3 valence quark baryons, or there were these quark antiquark mesons. And you look at that and you say, why are those the only compounds that you could make out of quarks and out of antiquarks? And that was a huge mystery. I mean, when I was a graduate student, I asked myself exactly the same question. And in fact, it's interesting, if you go back to the original papers of Gell-Mann or Zweig, they say, so this is our idea. Oh, by the way, you could also make all sorts of other combinations, but no one seems to have found them yet. You could make 4-quark combinations and 5-quark combinations and so forth. Mm-hmm. And it wasn't until 2003 that anyone had definitively seen something which doesn't fall into either the category of a 3-quark baryon or a quark antiquark meson.
Yeah. And so when you say you could make the 4 or 5-quark varieties.
Right. And those are the exotics.
Those are the exotics, but you could still in that combination could get to a -1 charge, right? With even and odd combinations.
Electric charge?
Yeah. So could you make a proton with, rather than 3, 5 quarks?
Yeah, so a pentaquark would be made out of 4 quarks and 1 antiquark. So you think through that and say, if I try an antiquark is minus a quark, then that has a net number of 3 quarks. Oh, so it would be a baryon, but it'd be a weird 5-quark baryon. So what you are asking is, could there be a 5-quark proton, with 5 actual valence quarks? And the answer is, well, yes and no. It depends on what attributes do you require to say, I've got a proton. If you say, all I really care about is I have a baryon that has +1 charge, there's a whole bunch of ways that you could make baryons that have +1 charge that aren't just 2 up quarks and a down quark, but they would not be the same as the protons that are sitting inside of our atomic nuclei. They are their own kinds of particles. So just like we were talking about, you can go through all these permutations of putting in different flavors, different species of quark and making different kinds of particles, the same thing would be true if you started adding in additional valence quarks inside of the hadrons. Those are different kinds of particles. They'll have different masses and different properties.
Yeah. So what do we know, Richard? So if you rewind time back, very close to the Big Bang, we would have had sort of a soup of quarks and electrons or something like that, right? So what do we know? Why was there a preference for this 3-quark combinations compared to others?
Well, that we don't even need to talk about the Big Bang for. That is something that we can use what we talked about in the first half of this talk, when we were talking about color charge as being the fundamental charge that's holding these quarks and gluons together. Now, there's a reason it's called color, even though it, as I said before, has nothing to do with literal colors. It has one very important mathematical property in common with colors, and that is, if you said, I'm going to take the 3 primary colors of light, red, green, and blue, how would I make a colorless combination of that? Well, there are 2 ways you could do it. If you had 3 primary colors, you could either take equal amounts of the 3 colors, red, green, and blue, and then that would give you white light. Or if you had access to, all possible ways of making colored light, you could take, say, blue and its anti-color, which is yellow. If you take an equal amount of blue and yellow, you would also make white light. And so those are exact analogs to what we've got with baryons and with mesons. A baryon has 3 quarks, each of which carries a color charge, which you could say, okay, well, one of the quarks is carrying a blue color, one of them's carrying a red color, one's carrying a green color, together colorless. Great. How about a meson? Okay, well, I've got a quark that's carrying a blue color and an antiquark that's carrying its anti-color, which is yellow, and that also makes a colorless combination. Perfect. So then the only thing you have to do is say, wow, okay, so that works out really well. So why do we have to stop with 2 or 3? Couldn't we do the same sneaky color wheel trick with 4 or 5 or 6 or 7? And the answer is yes, absolutely you can. It's just a matter of, can you actually make something like that in an experiment? And the odd thing about it is it took decades before people were sure that they actually had done that.
Is it an energy problem? Because ultimately there appears to be a preference for the 3-quark combination, right? Is that sort of the lowest energy situation?
It seems to be the case. And in fact, you were talking before about heavy quarks versus light quarks. It seems to be much easier to find the exotic particles once one or more of your quarks inside of the hadron is heavy. So it seems they tend to stand out more. When you only rely on making things out of light quarks, there are so many ways of making excitations of them that when you try to catalog them, that you just have this dense forest of excited hadrons. You don't know which ones are exotic and which ones are ordinary. It becomes very tricky to sort them out. But once you get up to the heavier quarks where you think you know how to figure out which particles, which conventional particles should exist, then you can say, wait a second, I've got one too many particles to fit the conventional scheme, or I've got an electric charge that doesn't fit the conventional scheme, or I've got some other attribute that doesn't fit the conventional scheme. That's when you say, maybe I'm looking at an exotic hadron.
Yeah, so I'm trying to get a very superficial understanding of this, Richard. So I understand intuitively that the mass of a proton, kind of a typical proton with the up and down quarks in them, is largely coming from the energy inside it.
Right.
And when we go to this more exotic quarks like a strange charm, top and bottom, there is less energy, there is more mass in the particle itself. So it almost sounds like a substitution.
It's not a substitution. It's saying that the amount of energy in the gluon field that's holding together is the same, whether you're talking about a light hadron or a heavy hadron. The difference is in a light hadron, it's like having these little flies that are stuck in this honey or amber. And that honey or amber is making up most of the bulk of the thing. Whereas if you have a heavy quark hadron, it's the same amount of honey or amber, but now you've got bowling balls stuck in it. And so it becomes easier to find out, what are those bowling balls doing? So you see the difference. It's like, with the original case where it's just a little fly stuck in the amber, it's very hard to figure out if you're looking at something where it's just the simplest possible combination, or they're doing some funky, additional excitation that you can't quite figure out. Whereas if you've got these big bowling balls, then it tends to be much easier to figure out what their configuration is.
Okay, so these exotic particles, then they will be much heavier than a typical particle.
Oh yes, definitely. And in fact, the first exotic particle that was definitively discovered back in 2003 is called the X3872, and that number 3872 refers to its mass, which happens to be about 4 times the mass of a proton or neutron.
And do we have an estimate of sort of the composition of the universe? What percentage of the universe might be those types of particles?
Well, these particles have short lifetimes. So that happens to be the case for almost all the particles that you could think of. So when you were asking early on, do we have to worry about hadrons other than protons and neutrons in everyday life? Those are the ones that are either stable or have very long lifetimes. You get to a point where you have lifetimes for some of these particles that can be on the order of, say, 10 to the minus 23 seconds, which is ridiculously small, but it is still possible to study these things, and you don't really understand how strong interactions work until you say, wait a second, this is a prominent attribute of what's going on in strong interaction physics. So even though they have a very short lifetime, I better figure out what's going on here.
Yeah. And so the exotic ones don't stay around. And so if they're produced in some phenomenon, like a supernova or something like that, if they're produced, they will die away.
Right. They will die away very quickly. And in fact, a supernova probably doesn't have enough ambient energy to produce particles like this. So basically, so let's look at, say, something like the sun. The temperature at the center of the sun is 15 million degrees Kelvin. You think that's incredibly high. That must be a lot of energy. But it turns out to be not even enough energy to produce, some fairly light particles like muons that appear in cosmic rays and things like that. So these kinds of reactions that produce these kinds of particles are actually at higher energies than have existed anywhere in the universe except in the very, very, very early parts of the Big Bang.
Yeah. But we can get those energy levels in the LHC.
We certainly can. In fact, you can get to much higher energy levels than the ones I'm talking about. So again, let's talk about this 3872 I talked about. So that was 4 times the mass of a proton or so. The Higgs boson is, let's see, it would be something around 140 times the mass of a proton or neutron. So it takes a lot more energy to make something like that. So the cool thing about it is that even though the Large Hadron Collider was put together in very big part to find the Higgs boson, the place where it has been the most successful in finding new particles is actually at a much lower energy scale. And the Large Hadron Collider is only one of several facilities that are finding these new exotic particles. There's also a very active program going on at a collider in Beijing, and then there's another one that is going on at a collider that's outside of Tokyo, and then there are American programs that are starting to study these particles as well in different energy ranges. So it's kind of cool in a way that, everyone immediately says, okay, let's go find Higgs bosons. But there's a lot of undiscovered physics happening at lower energy scales than that by a factor of 100.
Yeah. I also saw, I don't know if this has been shelved or not, there was another plan near Geneva to create a bigger accelerator. Do you know if that is still
well, there's going? Always plans to look at the next bigger accelerator, and it always depends upon funding levels. But if you're taking this seriously, then you perform studies and you figure out what would be the parameters of this machine and what would you hope to find, and do you have no-lose theorems that say no matter what happens, I'm going to either prove or disprove something, So these are decades-long processes, and similar ones are going on in other parts of the world as well. So the LHC by itself is going to be running off and on till at least 2030 and probably into the mid-2030s. So there's no worries about particle physics around the globe shutting down anytime soon. It's just a matter of are we ready to invest in the next level up?
Yeah. 10 to the power minus 23 seconds lifetime, you said, for this exotic particles. So there cannot be any sort of practical applications for them, right?
Well, you never know. I mean, so let me give you a historical analog. Way back in the early 19th century, there was a scientist / engineer in Britain by the name of Michael Faraday who was talking to Queen Victoria, and he was showing her some of these great new discoveries in electricity, and at one point he showed her what was the equivalent of what would become the electric motor, and they didn't know what was going to come of this. And Queen Victoria says, what use does this have? And he says to her, Madam, what use is a baby? We don't know what people are going to be doing with this 50 or 100 years from now. We pursue this because we love the science, so we want to know what is going on. practical applications happen when you don't expect them. So you can't always judge what you're going to be studying based on what the immediate applications are going to be.
Yeah. So I picked up with your recent paper, Richard. So this is about you call it Dynamical Diquark Model. So could you explain what that is?
Sure. So now that we're starting to get evidence that we have at least these 4 quark called tetraquark and 5 quark called pentaquark states, the question is, how are the quarks arranged in them? What is the structure of these things? And you might think, well, the most obvious thing you could think of would be to say that they are like little molecules of a pair of mesons, or a meson and a baryon, or something like that. And if it turns out that their mass is sufficiently close to the sum of the masses of those 2 particles, then you'd say, yeah, that makes sense. It could be a bound state of those. But there are others that just don't seem to match the attributes of being a molecule of mesons or baryons. And so you say, well, how would you end up with something in which all of these particles are strongly coupled together, but it isn't just an ordinary molecule? And one possibility is to look at how they were made and say, well, there's a lot of energy when these things are created. Either you're starting with a really heavy quark that's decaying to a somewhat heavy quark that's much lighter, or you're smashing them together in a collider, so there's a lot of ambient energy going on. And so you'd say, how would you create something that has a substructure that isn't just this ordinary molecule? Now, it turns out that this color interaction of quarks is very interesting. If you were talking about electric charges, you say, well, the rule of electric charges is very simple. If they have opposite charges, then they attract. And if they have like charges, like positive, positive, or negative, negative, they repel. But with color charges like you have on quarks, it turns out that there are configurations where quarks can be of the same type. It can be 2 types of quark of differing colors and they still attract. Or you could have 2 antiquarks of anticolors where they attract. Those are called diquarks. And you'd say, well, maybe what's going on in some of these processes where you're getting weird structures is that you're actually creating, say, 2 quarks and 2 antiquarks, and the 2 quarks are attracting through this weird diquark attraction. The 2 antiquarks are attracting through a diquark attraction. And because there's so much energy, they're flying apart from each other. But these diquarks or anti-diquarks themselves carry a net color. And so by the confinement property we've been talking about, they can't fly off as free particles. They're going to get stuck. What they're going to do is they're going to eat up all the kinetic energy that occurred in their production and turn it into the potential energy of the glue field that holds them together. And in that way, you end up with an extended object, which nevertheless, all the parts of it are all still strongly bound together. And that's the essence of what's called this dynamical diquark picture. And then once you have that, then you have to figure out, okay, well, how would I actually describe that mathematically? What kinds of interactions would be involved? How can I predict things? You turn that idea of a dynamical diquark picture into a dynamical diquark model. So that was my contribution to this field.
Yeah, it's fascinating. I don't know if I quite understand it, Richard. So if I take something that has 2 quarks and 2 antiquarks, you could envision a colorless state. But what you're saying is that you could also envision 2 sort of states combined together, and neither are really colorless.
Right. So overall, it takes the whole system, all 4 or 5 quarks, in order for it to be colorless. But it has these 2 pieces, these 2 quasi-particles, they're called diquarks, that are flying apart from each other. They carry a color charge themselves, so they can't fly off forever. But so they're stuck. So the diquark is stuck, in terms of having to stay in the same hadron to the anti-diquark, but they can get some distance apart from each other before they get stuck. So you end up with an extended object, a diquark at one end, an anti-diquark at the other. But all of the pieces, the two quarks and the two antiquarks, are all still feeling strong interactions amongst themselves.
And so just counting the quarks is not sufficient information. There's almost sort of an evolution of that particular particle that you have to worry about.
Well, that's the way I think about it forming. It has to exist. If such a thing exists, it would have to exist no matter how you produce it. But the easiest way of thinking about how you would produce such a thing is by means of the picture that I was describing so far. So if on the contrary, you were to just take two quarks and two antiquarks and stick them together, with nothing else happening, in a small space, they would overwhelmingly say, no, I'm just going to form two mesons, and that's the end of the story. And I'm saying that if you produce them in a configuration where you can form a diquark and anti-diquark before that happens, then you have some probability of forming this much more exotic state.
Right. Yeah. So presumably, I mean, if this is doable, then you actually have a process by which you can create all sorts of exotic.
Yes. And this is a very interesting idea, because it's a bound state that isn't a molecule. I mean, it's a weird thing that only lasts as long as it takes for the quarks on one side sitting in the diquark and the antiquarks on the other side in the anti-diquark to basically recognize, wait a second, I'm not a stable state. I have to decay. And so they have to recognize that, the only way for me to decay is to form a meson out of the quark from one side, the antiquark from the other. And so you see, that's something that's very different from an ordinary molecule.
Yeah. And so in conclusion, Richard, you're doing a lot of work in this area. It seems really fascinating. But if you look forward 5 years, I don't know, I mean, like you said, a lot of plans about bigger accelerators and so on. Funding is definitely going to control that. What do you see in terms of, or sort of speculation, next 5 years? How far can we go?
Well, this field doesn't depend on there being a bigger accelerator. This one, there's going to be, I can say without a doubt, there is going to be dozens and dozens and dozens more of these exotic states discovered. I was doing a count the other day. We're now up to 50 of these exotics, starting with the one that was discovered in 2003. And even last week, one of the collaborations at the Large Hadron Collider put out a paper discovering 4 more of these things. So, you could just do a count and say, well, how many permutations are there? And once you do just the permutations of the quarks, how many excitation levels are there? This is an extremely active area in terms of experimental physics. And so it's an exciting place to be, because nobody has come up with a perfect organizing scheme of what these exotics are. There's an analogy, at least in part to this, which is, I talked about the discovery of the Quark model. Well, in the late 1950s and early 1960s, what was going on is that these smaller accelerators were cranking out new particles all the time, and people just had no idea what they were all about, how they were all organized. It was only when the Quark model was discovered that it all started to make sense. The interesting thing here is we don't even know if there is an equivalent of the Quark model to this. It is entirely possible that the real solution to what all of these states are is that some of them might turn out to be ordinary molecules of 2 mesons or a meson and a baryon. Some of them might turn out to be these weird diquark states that I'm talking about. Some might be some entirely different kind of mechanism for how they're put together. So this is one of those rare times when experiment is just plain outpacing theory in particle physics. It hasn't been like this for decades. And so this is a very exciting time to be working in this area.
Yeah, does it throw a wrench into the standard model that was, sort of very
Yeah, I mean, so
together?
the interesting thing about this is all, as far as we know, standard model physics. In a way, exotic hadrons are the most slightly understood part of the entire standard model. I mean, we know what all the basic particles are in the standard model, but here we're finding out there are weird new ways of putting together some of them, and that isn't entirely settled yet.
Yeah, it's a bit like we went from fundamental to more fundamental particles, and we reached the quark regime, and now I think your work and similar things are basically saying we now have this foundational blocks, and we can build a lot of things with it, not just the ones.
That's exactly right. Somebody gave you a 1,000-piece Lego set and suddenly find that you can make a Sistine Chapel with it.
Right. Excellent. Yeah, this has been great, Richard.
Oh, you're very welcome, Gil. Thank you for inviting me.
Yeah, bye.
This is a Scientific Sense podcast providing unscripted conversations with leading academics and researchers on a variety of topics. If you'd like to sponsor this podcast, please reach out to info@scientificsense.com.